Yes, Sukanya, we are ready to go.
Okay, I'll just share my screen. Is my screen visible?
Yes.
Okay. Hi everyone. Good morning. So in this sessions, we'll be covering the hardware and sensor network protocols. So when it comes to hardware interfacing for IoT, be it Arduino, be it Raspberry Pi, or be it any other board with sensors, we mostly rely on the good old serial communications, which is usually the UARTs or the I2c communications of the SPI buses. So I'll cover these three protocols: UARTs, I2cs, and SPIs from the open source tutorial provided by Sparkfun Electronics. Post that, we'll be seeing a bit of a simulation demo on I2c, on SPI, as well as on UARTs. We will see, we'll mostly see M2M communications using Arduinos, using Raspberry Pis. It would be a mixture of simulations as well as some blog posts again on the internet that describes the uh, circuit diagram. The reason for using blog post right now or simulations board is for you to see the circuit diagram and the connectivity, the wirings between each of those devices. Well, otherwise, with if I had to show you on a hardware setup, physical hardware setup, it would be difficult for you to comprehend the circuit wirings. All right. So as we have many of you on the call, so we'll just get started. Starting with the good old serial communication. So what we have here, okay, so embedded electronics, basically the IoT applications part of it, is mostly about interlinking circuits like two hardware boards or connecting boards with sensors, right? And that creates basically a symbiotic systems of sensor networks. So in order for those individual circuits to exchange information, it is necessary for them to share a common communication protocol. So there are hundreds of communication protocol for data exchanges, but and in general, each can be separated into categories, ideally parallel or serial. And going by that basic foundations of parallel and serial communications will build up the will cover various communication protocols at the hardware level. So basically, people who are from electronics background would know like what a what parallel versus serial communication entails. So parallel interface basically transfer bits all at the same time, and the parallel interfaces usually requires buses of data transmitting across either 8, 16 or more wires. And of course, in case of parallel communication, data is transferred in huge amount and is generally binary in the waves of 0 and 1. Here is a simple example of a 8-bit bus controlled by a clock transmitting a byte for every clock pulse. So this is the clock pulse, and these are the bytes, and it's transmitting data between the bytes. Now coming to serial interface. So serial interface transmits every stream of data a single bit at a time. So it happens sequentially. These interfaces can operate on as little one as wire, usually never more than 4. So this is how it gets communicated one after the other. One bit, then the second one, then the third one, and here is the clock impulse for every bit transfer. So this is just a simple explanations of how it works. Now, talking about asynchronous serial. So over the past decades, dozens of serial protocols have basically been crafted to meet the needs of embedded communications. There is, of course, USB, Universal Serial Bus, um, Ethernet, and a couple of more well-known computing serial interfaces. Other very common serial interfaces are SPIs and I2cs, as we were discussing, but I'll cover those in depth in a while post this. And also the serial standards, basically we talk about every day. So each of these serial interfaces can be sorted in two groups. Either it's a synchronous form of communications or it's an asynchronous form of communications. So what happens in a synchronous form of communication? So basically in a synchronous serial interface, it always pairs its data line with a clock signal. So all devices on a synchronous serial bus shares the common clock. This makes it more straightforward, often faster serial transfer, but it also requires at least one extra wire between the communication devices. And such kind of synchronous communications are SPIs and I2cs. Whereas in the case of asynchronous communications, the data is transferred without the support of an external clock signal, which means that the transmission method is perfect and for minimizing the required wires, as there are no clock signals to be synced upon. But basically, it does mean that we need to put some extra effort into reliably transferring the receiving data, because as there are no clock signals syncing at the same time, it then becomes the responsibility at the program level to basically sync every mode of communications and capture every mode of communications that is being transferred and received. So basically, in this protocol, in this tutorial for UART, it's asynchronous transfer, and that's what we'll be discussing. For SPIs and I2Cs, we'll be discussing the synchronous mode of communications. So UART, I mean, when it comes to UART, the general thing is people say it as serial, and so I mean, UART is Universal Asynchronous Receiver Transmitters, but it's people consider it as a mode of serial communications. And yeah, so basically, you'll find anywhere if you need to just receive and transmit data with an RX and a TX interface, you can go for UARTs. But again, there are certain drawbacks of UARTs, again, which we'll cover when we go for the SPIs. For now, let's look at the rules of serial communication. So basically, in case of asynchronous serial protocol, it has a number of built-in rules and mechanisms that helps ensure robust and error-free data transfers. These mechanisms basically get for eschewing the external clocks such as data bits, synchronous bits, parity bits, and baud rates. So these basically ensures that the communications are syncing up and happen, and we are receiving the transmitted bits. Through these kinds of signaling mechanisms, these varieties of signaling mechanisms, you will also find that there's not only just one single way to send data serially. These protocols, of course, are highly configurable. So when we code, let's say, an Arduino and put the serial mode of communication to 9600 baud rates, then we want the serial monitor to be also synced up to 9600 baud rates. Also, there are various baud rates on the Arduino IDE, which I I'll probably cover the Arduino IDE in brief post this particular tutorial, to show you the various kinds of baud rates that are possible. Anyway, so the critical, basically what we need to ensure while doing such kind of asynchronous communications is that both devices has to be on a serial bus and are configured to use the exact same protocol. This needs to be ensured. Once we can ensure this, then we have a communications mode established between the hardwares and your sensors, or in case of M2M communications between two hardwares, or a mesh of hardwares. Anyway, so talking about baud rate, again, those who are from an electronics background would know this very well. So the baud rate basically specifies how fast the data is sent over a serial line. It is usually expressed in units of bits per seconds. So if basically if we invert the baud rate, we can find out just how long it takes to transmit a single bit of information or single bit of signal. And this value determines how long the transmitter holds a serial line, high or low, and at what period of receiving the device samples its line. Baud rate basically can also be just about the value within reason. The only requirement is that both the devices should be operating at the same baud rate. One of the more common baud rates, especially for normal communication stuffs or normal interfacing stuffs, is 9600 bps. Other baud rates can also be used, like specifically for a lot of SPI communications. People generally prefer 115-200 baud rates. There are other baud rates as well, but mostly we use 9600 baud rates for general transmission receiver communications, and for others we mostly go for 115-200 baud rates. Also, you, depending on what you would require and how you would want to configure, it's pretty customizable, and most of an Arduino IDE offers you a lot of other baud rates. So here are some examples. Anyway, so basically what happens, what we should be knowing is, for a higher, as the baud rate goes higher, the data is sent or received at a faster rate. But basically there are limits to how fast data can be transferred. You basically won't see the speeds exceeding this 115-200, and that is actually the maximum baud rate that is also available on the microcontroller level on the Arduino IDE as well. So if you get too high, you will begin to see errors on the receiving end, as clocks and sampling periods just can't keep up. So this is something that needs to be noted, that you can go to a maximum of 115-200 baud rates, and a minimum of, you can start with, and basic ones are 9600 baud rates. That pretty much does the job for the modes of communications. Anyway, so talking about the data, or the bytes, or the bits that are transferred. So each blocks, usually basically known as a byte of data, is transmitted. Transmitted is actually sent in a packet or frame of bits. So in case of internet mode of communications, data is transferred in the form of packets, and here data is transferred in the form of bits. Frames are just created by appending synchronizations and parity bits to our data. So it starts with 1 bit, then between 5 and 9 it's the data, and then the parity bits are 0, 1, and then it stops. So again, to understand this, maybe let's get into a little bit in depth. So the data chunk. So basically, the real deal of every serial packet is the data it carries, because we are doing this kind of communications for data transfer and nothing else. And then we ambiguously also call this block of data as a chunk, because its size isn't specifically stated. The amount of data in each packet can be set to anything between 5 to 9 bits. And the standard data size is basically 8-bit bytes. But other sizes have also their uses. A 7-bit data chunk can be more efficient than just 8-bit data chunks, especially if you're transferring the ASCII characters, which are 7 bits. Then once you decide on a character length, basically both serial devices also have to agree on the NDNS of their data. Is data sent more significant bits to least or vice versa? You just need to understand this. If not, otherwise stated, you can usually assume that the data is transferred in the least significant bit. So this is just the general or the basics of data transfer bits. But when you basically code a hardware, you don't get to see how things are working. I mean, these are just backend knowledges that helps you optimize your code or debug your code once you run into errors. It's as simple as that. Anyway, talking about synchronization bits. Synchronization bits are basically 2 or 3 special bits transferred with each chunk of data. They constitute the start bit and the stop bits. And as the name suggests, synchronization bits, this basically marks the beginning and the end of the packets, and they always there's always only one start bit, and but basically when it comes to stop bit, it can be configured to either 1 or 2. So usually it's usually we keep it as 1 stop bit, but it is at the programmer's discretion. When I say programmers, the software, the people who codes the hardware, basically, it's at their discretions what to leave it at. Talking about parity bits, basically parity bits is a form of very simple low level error checking. It comes in 2 flavors, either odd or even. To produce the parity bits, all 5 to 9 bits of the data byte are added up, and the evenness of the sum basically decides whether the bit has to be set or not. For example, assuming a parity bit is set to even and was being added to the data byte like this byte, which has an odd number of ones, and the parity bit would be set to 1. Conversely, if the parity mode was set to odd, the parity bit would be set. Then in that case, if the parity mode is odd, then the parity bit would be set to 0. Now, parity is optional and not very widely used. We don't generally go for parity bits while we code up an Arduino or a Raspberry Pi, as a matter of fact. It can also be helpful for transmitting across noisy mediums, but it also it also slows down the data transfer bit and requires both sender and receiver to implement error handling, just for debugging purposes. Anyway, now looking at the 9600 baud rate, it looks pretty much like this. So 9689 or 9600 baud rates has 8 bits, no parity, 1 stop bit, is one of the most commonly used serial protocols. So what would a packet or 2 of 9600 data look like? It would look like this. A device transmitting the ASCII characters, let's say O and K, would have to create 2 packets of data. The ASCII value of O, that's uppercase O, is 79, which breaks down basically to an 8-bit binary value of this 01001111, while K's binary value is 01001011. So all that's left is appending the synchronization bits, which are the start and stop bits. Then basically it looks like this: 0, 1, 1. These are the parity bits, the start bit, the stop bit, again the start bit, parity bits, and the stop bit. Oh, sorry, these are the data bits, the synchronization bits, and similarly for K, it's the same. Now, since we are transferring at 9600 BPS, the time spent for holding each of those bits, high or low, is 1 by 9600 baud BPS or baud rate, or 104 microsecond per bit. This is just for you to understand how fast the data transmission would work. For every bit of data transmitted, there are actually 10 bits being sent, a start bit, 8 data bits, and a stop bit. So at 9600 baud rates or BPS, we actually send 9600 bits per second or 960 bytes per second. So 8 data bits plus 2 synchronization bits, which is a start bit and a stop bit, that makes 10 bits. So at 9600 BPS, we are basically sending 960 bytes per second, which is 960 divided by 8 plus 2, 10. Now, talking about the hardware level, how serial and how serial communication would work. So every hardware, be it Arduino, be it Raspberry Pi, or any sensors that needs to be interfaced with this hardware, usually comes with a receiving pin and a transmission pin and a ground pin. So you connect the receiver with the transmitter. Let's say on the left hand side we have board 1, and on the right hand side we have board 2. So you connect the transmitter with the receiver of board 2 to board 1 and vice versa, so that actually serial communications could work and the data is received and transmitted properly. It is important to note that the receiver and the transmitter labels basically comes with an RX and a TX. RX and a TX symbol, and this generally identifies that one is a RX is a receiver mode and TX is the transmitter. So I will cover Arduino Pin Out and Raspberry Pi Pin Out as well. So you will see they have the RX and a TX mode. Only thing is that in case of Raspberry Pi, it's all general purpose input output, and you just need to know which GPIO pins stands for what. So I'll cover those in a while. So basically the receiver from one device should go to the transmitter of the other, and vice versa, as I was just explaining. And for powering up, the VCCs needs to be connected to VCCs, and of course ground needs to be connected to ground, otherwise you'd run into short circuit. Then there's MOSI, and also MOSI pins should be connected to MOSI. So we'll cover what MOSI is in a bit. But basically, you just need to take, while making the interface between hardware or sensors or between two hardwares, you just need to be careful on which pins you connect, because otherwise data won't be transmitted at all. A serial interface basically a serial interface where both devices may send and receive either full duplex or half duplex data. So when we say full duplex, it means that both devices can send and receive simultaneously. And when we are talking about half duplex, it means that a serial device must take turns in sending and receiving. So in case of full duplex, it's a two-way communications happening at the same time. And in case of half duplex, basically what happens is one device sends, then the other device responds, and you just need to work in unison and just see which one is going faster. And if you have to configure the half duplex communications from a code perspective, you just need to configure it accordingly, so that once device one sends the input, then device two receives and then sends the acknowledgement. That's how you need to code. Some serial buses might just get away with just single connections between sending and receiving devices. For example, basically, you also can connect an LCD to the serial mode of communications. And that's how data will be transmitted. Like if you want to get the output of your if you want to get the output of the program that you've coded, you can just connect an LCD in the serial mode of communications with your hardware boards, and that would just give you the output. All you just need to do is again go back to the programming end and just configure it. So these are pretty much how data is transmitted, the hardware implementations part of it, and so basically when a microcontrollers and other low-level ICs are usually ICs communicate serially, they usually do a TTL, which is a transistor to transistor logic level communications. So TTL serial signals exit between microcontrollers voltage supply range, so usually between 0 to 3.3 volt or 5 volt at the max, and this is pretty much the standard electronics assumptions, like not assumptions, the limitations of voltage. A signal at the VCC level is either 3.3 volt or 5 volt, which indicates an ideal line, a bit of value 1 or a stop bit. A 0 volt, which is the ground signal, represents either a start bit or a data bit of value 0. So you have 0 volt here, you have 5 volt here. If you power up the devices, it either goes for 3.3 volt or 5 volt, which are in ideal state, and then then you have the start bit, which is of course 0, and then these are the data bits, and then here you have the stop bit, and then again it goes to ideal state. Now, basically, for an RS-232, which can be found in most ancient computers and peripherals, which are not used now specifically, but just for understanding, it's basically a transistor to transistor logic serial flopped on its head. RS-232 signals usually range between minus 13 volt to 13 volt, though the specs allows for anything from plus minus 3 volt to plus minus 25 volt. So in that case, you have a minus 13 and a plus 13, and here is the ideal mode. So basically minus 5 volt to 13 volt, etc. indicates the ideal time, a stop bit or a data bit transfer of value 1. A high RS-32 signal means either a start bit or a 0 value data bit. All right, so here again you have the range between minus 13 and plus 13. These are the ideal modes. These are the data transfer start bits and the stop bits. Now, coming to UARTs, the much awaited receiver and transmitter protocol, or the serial protocol that we would be covering with a few examples. Okay, so basically UART stands for Universal Asynchronous Receiver and Transmitter. It's basically a block of circuitry that is responsible for implementing both implementing just serial communications. Essentially, the UARTs act as an intermediary between parallel and serial interface. On one end of the UART is a bus of 8 or so data lines plus some control planes. On the other side are just 2 wires, which are receivers and transmitters. So this is a typical UART interface, parallel on one end and serial on the other end. So mostly in case of boards like Arduino and Raspberry Pi, we have the serial mode of communications, RX and TX. UARTs basically do not exist in just standalone ICs. They are most commonly found inside microcontrollers, which again, Arduino to be more specific, also in Raspberry Pis as well. You will basically have, before buying, if you want to check, I mean, generally Arduino, all versions of Arduino, since it's a microcontroller, has the UART RX and TX, but you could also read the data sets. If you are going for other microcontrollers or microcomputers per se, like ESP8266 or let's say Samsung ARTkit or NVIDIA Jetson Nano, then in that case, or simple MicroPython boards or other boards, just read the data sheet to understand what kind of pin configurations they have. Okay, so so basically, Arduino Uno uses an Artmega 328. Arduino Uno is the go-to board for starting any prototyping. If you are new to IoT applications, setup, just buy an Arduino Uno board. But there are limitations of these microcontrollers because it does not have Bluetooth or Wi-Fi or as a matter of fact, any mode of communications except the capability to run for UARTs, I2cs, and SPIs. Okay, whereas Arduino Mega is built on Atmega 2560, and as the basically as the R&T acronym dictates, UART is responsible for both sending and receiving serial data. On the transmit side, the UART must create the data packets, appending sync and parity bits, and send the packets out to the TX line with precise timing. And another thing that you would need to understand is on the receiver end, UART has to sample the RX line at rates according to the expected baud rate. So while doing this serial mode of communications with UARTs, you need to specify, you need to be careful of the baud rates both on the transmitter and the receiver side. And this is an example of internal UART block diagram, which we would be covering it in depth because it's not quite relevant for this session. Just a few more things to understand before we move on. So Arduino, while coding for Arduino, you have something called the software serial library. That basically enables the serial mode of communications. And a few common pitfalls to remember while doing this mode of serial communications is receivers needs to be receivers needs to be connected. The RX button of the receiver side needs to be connected to the transmitter button of the transmission side, and vice versa. This needs to be careful. I mean, if you just connect RX to RX, TX to TX, it won't work. Okay. So yeah, and also you need to see the baud rate mismatch. If there's a baud rate mismatch, you would get inputs like this in your serial monitor, which is mostly because the speed and the character synchronizations is not possible. So ensure that you have both baud rates correct at the same point of time. Bus connections needs to be ensured. So you have this transmitter 1, you have this transmitter 2, and you have this receiver. Ground always needs to be connected to the ground, and the transmitter should be connected and the receiver should be connected. Ensure that you are connecting it correctly. Okay, and then you also have two receivers. Again, ensure the fact that you are connecting it correctly. Okay, these are only a few considerations when it comes to UART protocols. If you get these things correct, then your circuit will work absolutely fine. Okay. Now I'll just stop my sharing for just a minute. I'll just log into Tinkerboard to show you Tinkercad to show you some simulations. Meanwhile, feel free to ask any questions if you have in terms of Arduino, Raspberry Pi, and what you would see. Oh, before that, let me pull up the Arduino pin diagram for you, and also the Raspberry Pi pin diagram for you to show the input-output pins. Yeah. So this is the Arduino Pin Out Diagram, right? So this is an Arduino Uno, and here on the left hand side you have pretty much the this pin is ideal. Then you have the uh, voltage pins. This is a reset pin. This is an IO input output reference pin. This is a 3.3 volt pin, 5 volt pin, then ground. Then you have again another ground, and this is the V input. Then we have a series of analog pins, which are also used for other modes of communications. Then on the right hand side, we have AREF, then we have ground, then between pin 13 to so all of these pins are digital pins. Between 0 to 13, all of these are digital pins, or and specifically these are PWM pins for pulse width modulation. Again, all of these.
Sukanya,
Yeah.
excuse me. Can you slightly increase zoom of the browser by Control Plus? That would be nice for the participants to get an idea. Yeah.
Yeah.
Okay, thank you. Yeah. Little low.
I've just zoomed 200.
No. Go to as a for that Arduino block diagram itself. Otherwise, you can minimize it. Not a problem, because it may create a problem for you to.
Okay.
Display.
I did zoom out. I zoom out.
Yeah.
Right. So I zoom to 300%, as you see the
Yeah.
as you see this,
You make it,
right?
make it 200. You make it 200. That is sufficient. Yeah.
But is this visible right now? This diagram?
Yes. This okay. This is okay.
Yeah. Cool. Okay. Fine. So where was I? Yeah, so these are the analog pins, these are the digital pins, and between 0 to 7, it also serves as PWM pins. The way to read this is, okay, so this is an Atmega board, and the reference of the Atmega A328 is given here, pin out references. And one thing to remember is this notch is basically starting from 1, right? And then it goes like 1, 2, 3, 4, 5, 6 until 14 here, and then it starts from 15 until 28 here. The pinout references are given here. Anyway, so Atmega here is referenced in these pinouts. So this basically is the microcontroller that is the brain of the Arduino Uno, and these pins are useful for connecting your sensors or any other devices that comes across. Now, this is basically for SPI communications, sorry, I2c communications, and here we also have the pins which could be used for SPI communications, which we'll cover in a while. And just see the references. So anything that's black is ground. These are the power pins, and then we have the control. These also serves as the control, the yellow ones, and these are the physical pins. So digital and analog are the physical pins for interfacing the sensors or devices on digital or analog level. Then we have PWM pins, as we mentioned here, right? And sorry, PWM pins are these ones. These are the IDE pins, and serial pins are these many, because this is for UARTs. This is for, these are for I2cs and SPIs. And of course, these gets connected, these are referenced in the IDs. These pink ones, 14, 15, 16, 17, 18, 19, and here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, until 13, and 18 and 19. You can reference this pin on the IDE while you code the program. So we will see that example in a while. Anyway, yeah. So as I was referring to, the 5 volt and the 3.3 volt, which is essentially here, forms the regulations or the voltage inputs. The ground pins, which are on both the sides, one is two is here and one is here, is for ground. And there's a reset pin which resets the Arduino, and there's an IO reference pin. This pin is the input output reference. It basically provides voltage reference at which the microcontroller operates. So IO ref pin is this one. Okay. Now, as I was talking about, these are analog pins. Arduino Uno has 6 analog pins, which you could connect any sensors to in an analog mode. Like let's say your DHT22 sensor, which is a combined temperature and humidity sensors, can operate in both digital as well as analog mode. So you can connect in either the analog pins, you can connect that sensor in either the analog pins or the digital pins. Now, there's a possibility to do analog to digital conversion as well, basically within the Arduino itself. Arduino pins A0 to A5 are capable of reading analog voltage, and on Arduino the ADC has 10 bits resolutions, meaning that it can be represented using analog voltage by 1024 digital levels. The ADC converter, or the analog to digital converter, converts voltage into bits, which the microprocessor can basically understand. Okay, now Arduino Uno, these are the digital pins on the right hand side. So it also translates to, okay, let's just see the reference. Pin 0 to 13 of the Arduino Uno, 0, 13, serves as the digital input output pins. Pin 13 of the Arduino Uno is Arduino Uno has a built-in LED. And LED, for when you connect the receiver and the transmitter, these two blinks up. When you power up the Arduino, this blinks up. And this is also an inbuilt LED indicator within the Arduino. Okay, so pin 13 is generally connected to the built-in LED. And in the Arduino Uno, pin 3, 5, 6, 9, 10, and 11 has PWM capacity. It is also important to note that each pin can provide a sync up to 40 microampere max, but the recommended current is 20 microampere. So usually for anything, usually while sensor interfacing, it is advisable to go for 3.3 volt unless actually 5 volt is required. And the max voltage that can be applied by this board is 5 volt. The absolute max current provided on site from all the pins together is 200 microampere. All right. Now, basically, what does digital mean? It means that the voltage representation is in a binary format or a bit format, either 0 or 1. Digital pins on the Arduino are designed to be configured as inputs or outputs according to the needs of the users. Then digital pins are either on and off. When on, they are in a high voltage state of 5 volt. When off, they are in a low voltage state of 0 volt. On the Arduino, basically digital pins are configured as outputs that are set to 0 to 5 volt. Now, when the digital pins are configured as input, so by default, these digital pins are configured as output. Now, if you configure this as input, voltage is supplied from basically an external device. The voltage can vary anything between 0 to 5 volts, which is converted into bits, either 0 or 1. Now, one thing to remember is the thresholds. So if it's below 0.8 volt, it is considered as 0. If it is above 2 volt, then it is considered as 1. That means if it is above 2 volts, then at least your circuit can operate. You could see signals flowing. That is data being transmitted. If it is below 0.8 volts, then it does not work. I mean, you see it in an off mode, which basically translates to your circuit not working. Okay, let's cover PWM shortly. Pulse width modulations basically is a technique that encodes a message into pulsing signal. So like this. A pulse width modulation is comprised of two key components, frequency or the duty cycle. The PWM frequency dictates how long it takes to complete a single cycle period and how quickly the signal fluctuates from high to low. The duty cycle determines how long a signal stays high out of the total period. Duty cycle is represented in basically percentage. Now, in Arduino, the PWM or the pulse width modulation enabled pins produces a constant frequency of 500 megahertz, while the duty cycle changes according to the parameter set by the users. One practical use of these PWM pins would be, let's say, to control the voltage of an LED that is connected. Like you could with the help of pulse width modulations, you can put it to on and off mode, depending on the frequencies that you have specified, be it 25%, be it 50%, be it 75% or 100%. Also, excuse me. Also, let's say you have a motor connected to your microcontrollers or microprocessors. Then in that case, you could also control the speed of the motors using pulse width modulations. All right. Now, communications protocols. We just covered serial, so I'll just cover serial right now, and then once we cover Spis and I2cs, we will I'll get back to this and explain you the pins about Spis and I2cs. So basically, in this serial mode of communication, we covered what it is used to do. It basically is for serial modes of communications in the form of digital pins, 0 for receiver and 1 for transmissions, as well as USB mode of communications. So software serial and hardware serial, most microcontrollers basically have hardware designed to communicate with other serial devices. Serial ports uses a pin change interrupt systems to communicate. There's also a built-in library for software serial communications. In Arduino, you use the software serial. This is a built-in library. And here, these two pins are the Arduino references for serial mode of communications. I'll also pull up the Raspberry Pi pin diagram for your reference. Okay. So this is how the Raspberry Pi GPIO looks like. I mean, if you have seen the Raspberry Pi boards, you'll see there are various GPIOs on either side of the board. And specifically, there are 40 GPIO pins. 40 pins on either side of the board that has various functionalities. So this pin 1 is for 3.3 volt power, 2 and 4 here. So it goes like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. So 2 and 4 has 5 volt power, right? Here, okay, so the PWM pins are, okay, I'll just highlight each of 5 volt. Then we have grounds. These pins are grounds. Then we have pulse code modulations or the pulse width modulation pins, which is 19, 18, 20, 21. These four also act as pulse code modulations or pulse width modulation. But this pins also has other functionalities like clock, FS, digital input, digital output, all of those. Okay. Now, all of these are general purpose input output pins, which means that with the help of this wiring pipe, module, you can code your Raspberry Pi to configure to act on anything. Like if you want to connect sensors to one of these or many of these GPIO pins, then you just need to specify those pins, and you can use this wiring Pi library. It's a Python library. You can use this wiring Pi library to configure those sensors on the code sides on this particular GPIO pins. Okay, now we have the SPI pins. These are the SPI pins. The UART pins. UART pins are basically these. So this is used for transmission. Then there's transmission again here. Then there's receive as well, and the rest as well. So it has the clock pins as well as quite a lot of unlike Arduino, it has more number of transmission receiver pins that enables you to attach more than one sensors at a time, more than one sensors directly on the board. Whereas if you use a breadboard for Arduino, you can connect multiple sensors in the serial and in the receiver and transmitter board. Okay, so, and these are the I2c pins, data clock, EEPROM data, and EEPROM clock. So basically, again, for I2c, there's a module called I2c tools that basically does the job. For UART, again, just use wiring Pi and it does the job. For SPIs, here, use this. DT overlay configured in this file for running SPIs on Raspberry Pis. Okay, now that we covered pin out diagram, I'll just cover briefly what I2c communication is all about, and then UART, and then we'll jump into the demo part. So talking about I2cs, we'll again use a SparkFun tutorial. Yeah. So in this tutorial, basically we'll be talking about the I2c Communication Protocol. The way it communicates is, let's say you have controller 2 and then peripheral 1, peripheral 2. The SDA and SCL pins are responsible for I2c mode of communications. I2c stands for Inter-Integrated Circuit Protocol, and this protocol is intended to allow multiple peripheral digital circuits to communicate with one or more controller chips. Like the serial peripheral interface, SPIs, it is only intended for short distance communications within a single device. Also, like asynchronous serial interface, such as RS-232 or UARTs, it only requires, unlike these, it only requires, like UARTs, RX and TX, it only requires 2 signal wires for exchange. For SPIs, we would need 4 wires, which I'll come to in the next tutorial. All right. So why should we use I2cs basically? So to figure out what we want to communicate over I2cs, it is essential to know the drawbacks of the RX and the TX mode of communications. So basically, in serial ports, serial ports are asynchronous, which means that no clock data is transmitted. Device using them should agree ahead of time on the data rate. Otherwise, communication goes haywire. The two devices must also have clocks that basically are close to the same rate, which means which remains so excessive difference between the clock rates and on either end will cause garbled data. So that's what. So as I was saying, for UX, as it is asynchronous, there is no clock synchronization, without which, if there is no clock synchronization and if it is not taken care of particularly, you will see encrypted data, like like I showed you here, like these lines. Okay. Now, asynchronous serial ports basically requires hardware overhead. The UART at either end is relatively complex and difficult to accurately implement in software if necessary. At least one start and stop bits is a part of each frame of data, which means that basically 10 bits of transmissions are required for each 8 bits of data sent, which is the data rate. Now this is about memory consumption. So in UART we saw every data is transmitted with 8 bits, but it also has an additional 2 bits for every data that is transferred. So let's say if you transfer hello world, HELL also, each of these words, HELLO, all of these comprises of each 8 bits. Now add 2 more bits to each of these words. That increases the data size and hence the transmission size when it comes to larger data. Okay. Another core fault in asynchronous serial ports is that they are inherently suited to communications between 2 and only 2 devices. When it is possible to connect multiple devices to a serial port, bus contentions where 2 devices attempt to drive the same line at the same time. It's always an issue and must be dealt with carefully to prevent the damage of the device in questions. So basically, what they're trying to say here is UARTs are suited for only 2 devices, suited for communications between only 2 devices. You cannot essentially form a mesh of devices for receiver and transmitter for just normal UART communications. Why? Because if 2 devices target the receiver and the transmission line at the same time, then it causes a deadlock situations, in which case bus contention needs to be configured so that this issue does not arise. But ideally, in a practical scenario, it is difficult to communicate more than 2 devices on a UART mode of communications. Finally, another drawback of UART is the data rate. Basically, theoretically, there's no limit for asynchronous serial communications. Most UART devices support certain fixed baud rates, and the highest of this is usually 400 bits per second. But practically, it cannot go up to this. Mostly microcontrollers are configured till 115, 200, unless there are some advanced microcomputers that could operate at a higher baud rate. But microcontrollers mostly, on a practical sense, it goes up till 115, 200 baud rates. Okay, now, okay, what's wrong with SPIs? Before that, let's understand what SPI is, and then we'll come back to I2cs. Okay. So SPIs, or the serial peripheral interface, is basically an interface bus commonly used for sending data between microcontrollers and small peripherals such as shift registers, sensors, and SD cards. It uses separate clocks and data lines. Excuse me. It uses separate clocks and data lines along with a select line to choose the device we wish to talk to. Now, again, what's wrong with serial ports? We covered that. SPI is basically a synchronous solutions. So UARTs are asynchronous, and SPIs gives you a synchronous mode of communication. So SPIs works in a slightly different manner, which is the synchronous data bus, which means that it uses separate lines for data and a clock that keeps both sides in perfect sync. So it uses data as well as a clock that keeps both sides in sync. Hence, it requires four pins for communication. The clock basically is an oscillating signal that tells the receiver exactly when to sample the bits on the data line. So this clock is responsible for syncing the data bits. This could be rising to low or high or failing high to low edge of the clock signal. So basically, again, 0, 1, 0, 1, 0, 1, 0, 1, basis which, depending on the data that you're transmitting, the clock synchronizes. When the receiver detects that edge, it basically will immediately look at the data line to read the next bit. Because the clock is sent along with the data, specifying the speed here is not important. So here we are not much concerned with the baud rates because there's a clock. There's a clock that is responsible for syncing up the mode of syncing up the data communications. All right. Okay, so now looking at this diagram, there's a clock and there's data transfer bit. Here the clock, this is an ideal mode. Then we have the bytes transfer, and then again it goes to the next ideal mode. One reason for SPI being so popular is basically that the receiving hardware can just be a simple shift register. It need not be a microcontroller or a microprocessor. So shift registers are cheaper, and a piece of hardware that full up the UART, that asynchronous serial inputs, serial requires. Anyway, how is data received in an SPI mode of communications? So basically, what we have seen here is one-sided mode of communications. How do we send the data back to the opposite direction? This causes a little bit of complexity, but still can be done. In SPI, basically only one side generates the clock, usually denoted by either a CLK or a SCK or a serial clock. The side that generates the clock is basically known as the controller, and the other side, which just receives the signal is without the clock, is called the peripheral. There's always one controller, which is almost always your microcontroller, but there are multiple peripherals, which could be another microcontroller or sensors or a different board. All right. Okay. When data is sent to the controller, to a peripheral, it is sent on data line called COPI, the controller out or peripheral in. If the peripheral needs to send responses back to the controller will continue to generate a prearranged number of clock cycles. And the peripheral will put the data on a third data line called CIPO, which is the controller in or peripheral out. Okay. So when data basically is sent from the controller to the peripheral, something called COPI, which is the controller out peripheral in, gets activated. And when the peripheral generates the number of clock cycles, then in that case the opposite happens, which is the controller in peripheral out signal gets activated. Okay, so here if we are transmitting data from this side to this side, COPI and then CIPO. So what's happening here is, this is controller to peripheral and this is peripheral to controller. So these are the signals that are going. So when it goes from the controller to the peripheral, this side gets activated, which is COPI. And when it comes from the opposite end, then this side gets activated. And we see the signal as CIPO. Okay. Now, there's something called chip select in the SPI mode of communications. So there's at least one line So you should basically be aware of what chip select does. So this tells the peripheral that it should wake up and receive or send data, and is also used when multiple peripherals are present, and just chip select could be used to select the one that the controller would like to talk to. Okay, so here again, just modifying this a bit. While these two things happens, while COPI and CIPO happens, the chip select basically is sending signal to the microcontroller for receiving and transmitting data. After this is done, it again goes back to the ideal state. Okay, the chip select line is normally held high. When it is high, it disconnects the peripheral from the SPI bus. This type of logic is basically known as active low, and this is often seen when it is used for enabling the reset line. So when you click on the reset button, this kind of mechanism is usually seen. Just before the data is sent to the peripheral, the line is brought low, which activates the peripheral. When you're done using the peripheral, the line is made high again, which again goes back to the ideal state. All right. So when data is transmitted, it comes to low. When data is not transmitted, it goes back to the high state and stays in ideal. So this is an example how multiple peripheral communicates in the SPI mode of communication. So what is happening here is basically each peripheral needs a separate CS line. Excuse me. So here you would need multiple chip select lines, serial clock. Of course, one clock caters to all the peripherals, but each peripheral has to have one chip select line basis which you will be selecting the selecting which peripheral to communicate to. Okay, and in this case, some paths prefer to be daisy chained together with CIPO, which is the output of one going to the other peripheral, COPI of the next. In this case, basically, the chip select line goes to all the peripherals. One chip select line goes to all the peripherals. Once the data is sent, the chip select line is raised, which causes all the chips to be activated simultaneously. And so this is basically sequential mode of communications, and this is synchronous mode of communications, where communication is sent to all the peripherals at once to act at the same time. And here, depending on the requirement, we are sending the mode of communications. Let's say an example of this could be something like, let's say, okay, you have an Arduino and you have an Arduino sensor network, right? So when I say sensor network, let's say you have multiple sensors connected to one brain, the Arduino, for example. For now, let's consider brain. Okay, so you have temperature and humidity sensor. You have soil moisture sensor. You have rain sensor. You have let's say wind sensors attached to it, but you don't. But in one particular scenario, you don't need all the data together. So you just activate which one you require and accordingly gather the data, right? Also, consider the same example and consider a weather station where you are monitoring continuously the wind speed, the moisture content of the soil, the rain content, and the temperature and humidity content of the atmosphere, just for a specific reason. Let's say for irrigation purposes, and you need all the devices to communicate together at the same time. In that case, the second mode of communications, which has one chip select, comes in handy. Okay, now these are just examples of programming for SPIs. So you can use the shift in, shift out commands. Then Arduino IDE has SPI libraries that basically helps in doing the SPI mode of communications. And it pretty much looks like this. Once you transfer the data, there's clock. Once the data transmission is stopped, then the clock signal stops. So there are some advantages of SPI, which is like it is faster than asynchronous mode of communications, and the receiving hardware could just be a shift register. But in a practical scenario, when it comes to IoT, it generally won't be a shift register. Ideally, would be another set of hardware, which could ideally be a sensor or microcontrollers. And there are certain disadvantages of SPIs as well. It requires more signal lines. As we saw, it requires 4 signal lines, whereas in UARTs and I2cs, it was requiring 2 signal lines anyway. And then the communications must be well defined in advance. And you basically can't send random amount of data whenever you want, because it's a synchronous mode of communications. And the controller must control all the communications. And it usually requires a separate chip select line for each peripherals, which can be problematic. If in case, it just gets a little more complex if you require a separate chip select line for every peripheral that you connect to the hardware. Now, that's where I2c kicks in. So we covered what's wrong with UARTs. Here we'll cover what's wrong with SPIs. So here is one controller and here are 2 peripherals. So what happens is the most obvious drawback for SPI is, of course, the number of pins required, which is 4. And in case of multiple chip selects, it just keeps on increasing. Then connecting a single controller to a single peripheral with an SPI bus requires 4 lines, as we discussed. Then the rapid proliferations of pin connections makes it undesirable in situations where lots of devices needs to be connected to one microcontroller. So if it's a sensor mesh is nothing but sensor networks, but larger number of sensors attached to one microcontrollers, like network mesh or something of that sort. Okay, so also large number of connections for each devices can make routing signals more difficult in tight PCB layouts. And of course, so if you are designing your own hardwares, then well, designing and putting it on the PCB layouts is difficult. Then SPI only allows one controller on the bus, but it does support an arbitrary number of peripherals subjected to the drive capability of the device connected to the bus and the number of chip select pins available. On the other hand, SPI is essentially good for full duplex mode of communications, which means that sending and receiving can happen at the same time. And also it supports clock rates up to 10 megahertz, thus 10 million bits per second for some devices. Okay. Now, so this is when I2c kicks in. Few drawbacks of UARTs, few drawbacks of SPIs. And this is where I2c kicks in. I2c basically requires just 2 wires. You just connect the SDA to SDA and SCL to SCL. SCL is for serial, SCL stands for clock, and the SDAs are the data bits. Anyway, so like asynchronous serial, but this is, I mean, it just requires 2 pins like asynchronous serials, but I2c, but those 2 wires can support up to 1008 peripheral devices, up to 1008 peripheral devices at once. Also, unlike SPIs, I2c can support multi-controller system, allowing more than one controller to communicate with all the peripherals devices on the bus. Also, although the controller device can't talk to each other over the other buses and must make turns using the bus lines. This is something that needs to be noted. But it allows you to connect to multiple devices on the bus. Then data rate falls between asynchronous serials and SPIs. Most I2c devices can communicate at 100 kilohertz or 400 kilohertz. There is some overhead with I2c. For every bits of data to be sent, one extra bit of metadata, that is the acknowledge or the not acknowledged bit, which we'll be discussing later. It really must be transmitted just to acknowledge the fact that data has been transmitted. Okay, so previously it used to go by the name of Master Slave, which is now replaced with controller and peripheral, but the concept still remains the same. We necessarily don't need to talk about the history of I2c bus, because I mean, you can just go to this tutorial and read it. What we are more interested is now the hardwares. Okay, so now that I covered I2c and SPIs, I'll cover the pin out diagram a little bit more. So SCL, SDA, SCL, SDA, these are for I2cs. On the Arduino side, these pins are responsible for SCLs and SDAs. And here, these four are responsible for the SPI mode of communications on the Arduino. So going back, so SPIs, we have SS, SCT, which is serial clock, SS is slave select, MISO, master input slave out, and this is master out slave input pins. These are declared for the SPI mode of communications. Okay, and for I2c, we have the SCL SDA, which generally stands for SCL is the clock line, which is designed to synchronize data transfer, and SDA is the line that is used to transmit data. There's also ARF that we were talking about, this one. So ARF, I mean, this is basically reference voltage for analog inputs. There is the interrupt 0 and interrupt 1. Arduino Uno has 2 interrupt pins. Forgot where the interrupt pins are. Oh, here. INT1 and INT0, these two, 3 and 2, would alternatively act as interrupt pins. And there's external interrupt as well. An external interrupt is a system of interrupt that occurs when outside interface is present. So you can also, I mean, Arduino Uno is capable, has external interrupt enabled. You can use it depending on the requirement that you would need. Okay, now moving on to the Raspberry Pi. Yeah, all right. So moving on to the Raspberry Pi, the SPI pins are these, as I covered, 17. So on the left hand side, you have pin 11, 19, 21, 23, and 35 acting as the SPI pins. So you see there's MOSI, MISO, serial clock, MISO, then again here MOSI, and then serial clock. So 2 of each. There's also C0, C1. These are for controller interfaces, 0, 1, 0, 1. Sorry, 0, 1, 0, 1, and there's also 2 here. Okay. And subsequently, the I2c pins, data, clock, then the EEPROM data and EEPROM clock. These are necessary for I2c pins. At least, I mean, there's also something called I2c EEPROM, which we are not covering. So in case you're doing that mode of communications, these 2 pins comes in handy. But otherwise, these are responsible for I2c communications in Raspberry Pi. Okay, now I'll just give you a 1 minute break please ask me if you have any questions. Meanwhile, I'll just pull up the simulation environment for you to look into some examples. Feel free to ask me any questions. If you want to know practically where these are used, how could these be used, or something of that, then please. You can either unmute yourself or put your questions in the chat.
Yeah, rather than like if someone has questions, you can raise the hands or you can write down in the chat window so that we can take those questions as well. If
Right.
if you can raise your hand, that will be very nice. So we can go ahead in that way.
Sure. I'll just take another minute and then we'll start with the simulations. All right.
Yes.
So far, I don't see any questions in the chat. Also, I don't see any hands, I believe, right?
Yeah. Anyway, Sukanya, you can go with the simulation part. Maybe that will clear more. That will clear the idea, and they can correlate with their applications.
Sure. That's where I'm leading it. Just okay, fine. So. Is my screen visible?
It's coming. Yeah.
Yes. Okay. So, okay, this is an example of UART mode of communications, receiver and transmitter. So let me talk about the interface a little bit. So this is Autodesk Tinkercad. This particular piece of software allows for simulations of Arduino. At this present moment, this does not support, unfortunately, this does not support any other boards, possibly because of, sorry. Okay, so this does not support any other boards because of security issues, and that's the very general reasons why we don't have good Raspberry Pi simulators as well. Online simulators that could simulate the Raspberry Pi environment or the Raspberry Pi board. But there are a few here and there, but not quite up to the mark for proper demonstration. But this software, particular piece of software, is very good for Arduino mode of simulations. All right. So here we have two Arduinos. This is the transmitter Arduino. This is the receiver Arduino. Okay, and the grounds of each Arduino are connected here on the breadboard, and this. So, if you're familiar with breadboards, in breadboards, this line carries same signal, and this line carries same. So, plus and minus, this is and this side is carrying positive signal. On this side also, it's plus and minus, it's like this. Okay. And here, this part, these lines like this carry similar signals. Again, there's a divider between, and then again, these five carry similar signals. So here, these vertically it carries similar signals, and here horizontally it carries similar signals. Now there are two LEDs attached. So this is a blue LED, and this is an orange LED. Now, looking at the code, so what happens here is, let's look at the transmitter code. So you're using serial library, right? It's simple Arduino code. Even Arduino IDE pretty much looks like this. So we have the transmitter connected at the 8th pin, which is the LED on, which gives the signal for LED on. Then we do the setup. Pin mode 2 is connected to the anode of the LED, and is the positive leg of the LED. And there's a serial baud rate of 9600. Then we initialize a variable to 0 because we'll be using this variable for looping purpose. Then we put this variable through loop, and it goes on till 0, 1, 2, 3, 4 until it is less than 5. Then we do a serial write transmission to 7. Then we do a digital write to pin 2, which is high, and then we give a delay of 500. Then we keep looping until it is less than 5, and then we send the buffer and post that. So this happens all in loop. So this goes on till 5. 5 as in it starts from 0, 1, 2, 3, 4. And then we write the signal. We make the digital write pin, which is this pin, to high, and then the signal flow stops on the transmission side. You'll understand this a little more in depth once we start the simulation. Now let's look at the receiver code. So the receiving end is the RX8 incoming data array. Then we have the pin mode 12, which is connecting to the anode of this LED. We also, for this case, we have a serial baud rate of 9600. Then again in the loop, we say if serial.available is greater than 0, that means if from the transmitter side we get a signal, then we do a serial.println got it. That means we're just printing an output, an acknowledgement signal once we receive the value from the transmission side. We read the bytes, we write it, and then we clean the RX data if needed. If we don't get this, we just write that there is no signal. We enable the digital output 12 pin to be low, which means that this LED won't light up. Okay, now let's look at the simulation. Okay, so did you see the LED blink? I'll just restart. So you see LED is blinking for 5 and then it stops both. Okay. Now if I clear again, got it is the receiver sided. This is the transmission sided. Okay. So I am now at the transmission receiver. I'll just reset this and start. You see, LED on, LED on, LED on, LED on until 5 times. And also on the receiver side, we'll receive 5 signals that says got it, got it, got it, got it. Okay. Now if we change the code slightly to, let's say, 10, to let's say 10, and this is on the transmission side, and then we clear our serial outputs and then we start simulation. So we see 10 signals here. Similarly on the receiver side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 signals. So this is just the serial mode of communications, wherein we get inputs from the transmission side. And you see, okay, one more thing to notice here is the LED on the transmission side is not blinking, whereas the LED on the transmission on the receiver side is blinking, which means that the LED remains on the transmitter side for until it goes on for the entire loop, whereas every signal for the loop, throughout the loop that the receiver receives, it just gets activated and turns the LED on. So this is just a LED simulations. This could be replicated for any sensor devices as well, wherein you configure the sensor to transmit the signal, and on the receiver end you have another signal that acts upon receiving the transmission signal from the transmitter. Any questions here? Was this example clear at all?
Dear participants, you can write into a chat box, or I can unmute you all at the same time. Otherwise, raising hand would be good, actually. Otherwise, it will be mess. Yeah. Yes, Sukanya, what you wanted to say?
Yes, I just wanted to understand, like, if there are any questions. If not, then I'll just move on to another example, maybe.
Yes, you can move on to the next example.
Okay. So here is another example of UART, a little more complex. So what you see here is a temperature sensor attached on the analog pin. So the legs of the temperature sensor are, so this is the power button, this is the ground, and this is the data. Okay, and excuse me, and both the boards are connected to each other using the digital pins. And here, this is a piezo buzzer. We won't necessarily be hearing the buzzer in the simulations, but we'll see how it works. Let me try and do this. So this is another board. I'm just putting one on top of the other. Okay, so looking at the code, what we have is, so this is the second Arduino, this is the first Arduino. Okay, so looking at the code of the first Arduino, let's see what we have. We have we are specifying the temperature. We are inputting the value T. We are doing the void setup on the A0 pin, which is the input, and at a serial baud rate of 9600. Then we are doing a void loop, and then value of 97. Then we are doing serial write. In the serial monitor, we are writing the value with a delay of one millisecond, which is 1000, and then yes, printing the value on the serial monitor. On the pin 2, what we are doing is we are setting up for the pin mode 6, the piezo buzzer as the output. Then we are writing the digital write. Sorry. So this is the digital write pin to 6. Initially it is set to low, and it is monitor at 9600 baud rate. We put it to the loop. We put a delay of 1 millisecond. Then we we just take a variable to read the serial value. Then we do a delay of 1000, and then value of this serial read, right? And then again, for the next iterations, we just put a delay of millisecond, and that's how it continues. Okay, so if we start this simulation, we pick up the serial monitor. Okay, so you see Arduinos are powered up. You see the on button. You see the temperature is currently 97.55 now. If I change the temperature, here mode of serial. Sorry, see this.
Sukanya, your voice is breaking.
Okay, I'll just change my network. One second. Yeah, am I audible clearly now?
Yes, yes, yes.
Okay, great. So, so what's happening is this temperature sensor is receiving this transmitting this value to the. Sorry, it's the opposite way around. So this is the transmitter. It is transmitting the values, and the temperature sensor is getting and the temperature is getting logged in the serial monitor. So similarly, like if you piezo buzzer is nothing just but an actuator output, but again translating this to a real life scenario, maybe your transmitter on the transmission end you could have a remote signal, and on the receiver end you could have sensor networks and control those sensors through that remote. That could also be a possibility. Yeah, I mean, but UART is like too simple for that. We also have other wireless modes of communications which will come to at a later point of time. I mean, in the next session. So yeah, that's pretty much that. So next, in the next circuit, we'll talk about I2c Master Slave. So this is master. That means it is the controller. And this is the slave, that is, it is the peripheral. Okay, now let's look at the code. What this does is, you see, okay, the difference is, you see there's a button attached on the master side, and there's a LED attached on the slave side, which is the peripheral side. So on click of this button, LED will be blinking. So let's look at the code. On the master side, we just have a simple voice. We have configured the push button to A0. And we just have done the void setup using wire libraries. We just specified a variable int x is equal to 0. And then we put it through the loop. Wire.begin transmissions, then x.digital read. Just read it from the push button. Wire.write x, wire is just a library. That's why we need to specify the library to read it from that, and just write the transmission and just end the transmission with a delay of half a millisecond. Okay, and on the slave side, the code that we have is, we've configured the LED to pin 13. Then we have done the void setup, which is the begin rate and also the begin pin on which it receives the signal. They receive events, the baud rate at 9600, and then the pin mode LED outputs. Okay, then we have a void loop. We have inside the loop, we've just put a delay of 100, which is just like I guess 0.01 milliseconds kind of, if I'm not wrong, or 0.1 milliseconds. Anyway, then we have void receive end int, just like another variable where we take the wire reading. This read module takes the reading, then it prints on the serial monitor, and this is just checking if the value of x is equal to 1. Then the digital write pin, the LED pin should be like high, else the digital write pin, the LED pin should be low. Now, looking at this code, let's simulate and see where we are. You can't see that, so for that, okay, I believe you, yeah, okay. So both the Arduinos are plugged in. We see the on LED. The connection is for the analog signal, it's connected through these two pins. So this is the I2c pins, SDA and SCL, as we discussed, right? The ground pins are connected to each other. On one end, we have a push button, and on one end, we have LED. So we are receiving 0 signals since the LED is off. Let's try to click on this push button. What happens when we receive 1? Notice the LED. Notice the LED lighting up for every click of the push button. Did you notice we have a 1 signal, LED lights up? So LEDs are like hello worlds of the microcontroller environment. Again, a simple replications of this would be to have a master sending signals to slave for specific sets of actions. And on the master side, we have something, and on the slave side, we have a group of sensor networks that could be an ideal environment to replicate this issue. Another example, this is a little complicated example, but pretty much the same. Due to lack of time, I won't be going through the code because it's complex also at the same time, and it would require time to explain. But let me show you the simulation so that you understand what's happening here. Oh, before simulations, let me just explain. So this is the controller Arduino. This is the peripheral Arduino. And so what happens here is there's a potentiometer attached to each of the master and the slave, and there's an LED screen attached. And what happens is, once we change the potentiometer reading here, this will display on the slave. This change value will be displayed on the slave. And once we change the potentiometer value here, this change in value would be displayed on the master, which is this one, and slave is this one. So once we start the simulation, so you see, so this is the master, this is the slave. So once we change this value here, you see the slave value changed. Okay. Okay. And once we change the value here, you see the master value is changing. This is a typical example of two-way I2c communications. As we saw, I2c is capable of full duplex mode of communications, and this is a typical example of full duplex communications. Okay, so you get a fair idea of what's happening here. If you still want to see the serial monitored, so you see master received from slave 30, master received from slave 104. Then we see, okay, so now this is the master monitor. Now on the slave side, if we changed, it says slave received from master 38, slave received from master 96. So this is how it gets plotted on the serial monitor. Okay, just another example before we close off this session. So this is a typical example of an SPI. What is happening here is we have connected a push button, and the SPI, both the SPI boards are connected. Excuse me. Both the SPI boards are connected to each other, and these are the SPI pins that we discussed. Clock, meso, mosi, and SS. So this is how SPIs are connected. And looking at the code side, what happens is we just configure. We're just putting up the character buffer, and we just these are some initializations of some libraries, and then beyond that we do the setup. We begin the baud rate monitor. The monitor serial monitor baud rate is at 9600. Then we configured the pin mode meso to be output. Then we also configured the SPCR, which is not equal to SPE, and index 0. Then process false. Then SPI attached interrupt. We just check if the interrupt is attached. Also for ISR, SPI, STC vect, we do a similar kind of calculations, and then we put it through the loop for printing. This loop basically prints to the buffer, prints to the serial buffer, and this is the second SPI. Sorry, the first one that acts as a controller. So what we do is we just specify the buttons, we see serial rates, the clocks which are high, which are supposed to be high. Then we begin the baud rates, and also specify the serial begin. Then the characters and the digital writes, and SPI transfer C, then digital button writes. And if the button press is by default false. If it is not, then we get this one written, button pressed. Okay, so this covers UART examples, I2c examples, and SPI examples. Again, these were simple examples to demonstrate how you could, these are like ABCs, to demonstrate how you could actually configure your sensors on the these microcontroller boards such as Arduino and get it up and running. Okay, it's already 10, but feel free to ask me any questions if you have any.
Yes, if there are any questions from the participant side, please raise the hands. Otherwise, Sukanya, what we'll do, we'll take a break of 20 minutes. And by 10:20, we will again reassemble here for
Sure. Can we start the session at 10:30?
We'll start it by 10:20, please.
Sure.
Yeah, thank you. Right, so participants, already the link is being shared. Since this Sukanya is going to continue the session, so I request you to see the links that is available into the classroom, and we'll start the session by 10:20. Instead of like we are expected to close this session by 9:50 and start the second session by 10:10. By 20 minutes break. So, but here, since we have extended by 10 minutes, so we'll be starting late by 10 minutes. So 10:20 is the time to connect to the session, right? So I'm ending this session now. In the next session, we'll continue with Sukanya only, right? Thank you.
Thank you
very much. Yeah. So in the meantime, you can leave.
Yes.
Yeah. In the meantime, you can leave this